The next section we're going to be going over is about the method of undetermined coefficients. And like usual, we're going to start by talking about the general approach for this type of problem, and then we'll try applying it to some examples. So, So when we're talking about undetermined coefficients, this is going to be a method where we can find the particular solution to a specific group of equations. They're going to be constant coefficient, non-homogeneous, differential equations. And just as a reminder, what that looks like for constant coefficient means that we have some constants, a, n, times the nth derivative, and we just sort of keep multiplying by constants as we go down in the derivatives. a1 y prime and a0 y. And then because it's non-homogeneous, previously we thought about this being equal to 0, but now we're going to have some non-zero g of x, so some sort of function that can depend on x when we're solving this problem. And we know how to find solutions related to the left side of the equation. We've got those y1 e to the m1x through yn e to the mnx. And we do still have to use that information we learned about constant coefficient problems. But then we need one extra part where we find the particular solution y sub p that's related to that right-hand side. And in this case, so just so you know, y sub p means particular solution. And then once we have those pieces, we can write out the general solution, which is going to be y equal to c1 y1 down through cn yn, just like we'd have for the regular constant coefficient problem. And then all we do is we add that y sub p because of that superposition idea we discussed at the very start of like this chunk of videos. So, given that that's the problem we're solving, I want to outline for us the actual approach we'll use. And you know what? I'm going to go ahead and put it all on one page so you can see all the steps at once. So our approach is going to be that we let y sub p be some a times g1 plus b times g2, so on and so forth, where a, b, and whatever other letters we want to use are the undetermined coefficients that this method is named for. And then g1, g2, and any other functions we end up including here are sort of selected so that they're related to the g we see in the equation. And when we go through examples, that related to will become more clear. But this is one of those approaches where we assume what the solution is going to be, and then once we make that assumption, we plug it in. So our step 2 is going to be plugging y sub p into the ODE. Like other methods where we took this approach, we need to remember to take derivatives. Yp prime, yp double prime, however far is necessary to plug into the differential equation. Once we do that, we're going to want to group like terms. And by that I mean similar to or including G1, G2, so on and so forth. And what that's going to do is it's going to give us groups of coefficients that we want to set equal to each other. I know that this is a little bit hard to think about in theory, but I promise it's a really straightforward process once we start the examples. I'm going to leave a little star here for a note that we're going to discuss after the first example we do, so please leave yourself just the same as one line, however long that ends up being for you in your notes. And it's already done for you all in the skeleton notes. But after we do that, what we're going to do is solve a system of algebraic equations for those undetermined coefficients that we introduced. And then after we know what A, B, so on and so forth are, we can go ahead and plug in those values. To get our particular solution, y sub p, which we assumed was ag1 plus bg2, so on and so forth. And then we have the y sub p we need to plug into that general solution I wrote on the previous slide. So in order to do this, we have to discuss like what this g1, g2, and so on is. So I'm going to switch slides. Please pause if you're still writing. But that first step where we pick G1, G2 is not super well defined. And there's going to be three principles that we use in order to pick these values. And I'm going to tell you the first, and then we're going to return later on in our videos to the other principles. We'll kind of introduce them one by one. But our first rule is that we're just going to use terms that appear in g of x. So for example, if we had y double prime minus y prime minus 1 equal to 2x squared, plus 3x plus 4. When I write these examples down, I just pick random numbers, but then once they're in the skeleton notes, I have to make sure they're the same numbers. So if this was my differential equation that I was working with, when I pick my G1, G2, so on and so forth, I just grab every function that shows up somewhere in G. So I'm going to say, okay, I see an x squared, I see an x, and I see a constant. So instead of doing 2x squared, 3x, and 4, I just picked the most basic version of those functions. You won't hurt anything by making it 2x squared, for example. But since we end up multiplying by unknown coefficients, it just kind of makes all your algebra messier. So I do recommend sticking to this version that has no more numbers than absolutely necessary. And then I'd like you to leave space to just write one more thing that's about as long, and then one more that could take just like one extra line. So leave space for those two other things we'll discuss, derivatives and repeats, later in the videos. Let's see how we're doing. Okay, we're just about at 10, so I'm gonna hit pause here, and then in the next video we'll go ahead and do an example that uses this first principle.